everybody, my name is Deakin and today in this tutorial I will show you how to solve a problem called the cone problem with algorithm. I have a very simple and short way to solve it. So this task actually comes from one assignment in my university Deakin, which is from the unit called data structure and algorithm. This task actually have troubled a lot of my peer, and some haven't come up with a solution. Some come up with solutions that run really slow, or actually quite nice. But I think I have found the well, not exactly the most optimal way, but like a very good way which run really fast. So here's a code problem. You can just pause here, have a look at it, think about it, and try to solve it if you like to. Take some challenge. But if you're not, let's go with. So here's some example of the algorithm. It should like if the z is 1, it should return 1, 6 return 3, 47 return 2, 84, 89, 289 should return 6853. So to begin, how to solve the task, you actually need to find a pattern. Like you need to find a way that how can it gonna repeat itself. If it's not gonna have any rule, any way to repeat itself, this task is unsolvable. It's almost unsolvable. You need to find a pattern to make it. You can find to actually find a way to solve it. So you need to look at what the problem tells you. So the problem tells you all the number is the power 2 to the power k, and can have maximum 2 cones. So you can see something in common here is the number 2. So everything is divisible by 2. So continue with this. I have so there were a pattern to see. So the pattern is if the odd number, if it is an odd number with 2 and plus 1, so the result of 2n plus 1 will equal to result of 2 of n. And if it's an even number, 2n plus 2, the result of 2n plus 2 will equal to n plus 1 plus n. So plus the result of n. So the reason why it's like this because this. So if it's an odd number, which is shown here is 2n plus 1, it must have one cone 1 2 to the power 0 cone, which is equal to 1. This it must have one cone of this 2 to the power 0 and only this one only. So if you delete this cone, it only have 2n left, and if you divide by 2, it will have n. And it will be the same because everything is a power 2 or can have maximum 2 cones. So it definitely can be divided by 2. And you already minus the 2 to the power 0 cone, which is the only number or the only value that you cannot divide it by 2. So continue with the even number with 2n plus 2. The reason why are two cases because there are two cases of the 2 to the power 0 cone. One is when you don't have any cone, which is 2n plus 2, you just divide by 2 and equal to n plus 1. So but there will also be a case that it actually have 2 of the 2 to the power 0 cone. So it's actually we have to remove the 2 cone and only have 2n left, and divide by 2 we only have n. So the total weight of 2n plus 2 will be the result of n plus 1 plus the result of n. So that's the pattern. So actually just knowing that pattern with and 2n plus 2 equal n plus 1 plus n, 2n plus 1 equal to n, and 0 will equal to 1. You can solve it already with plain recursion. So with the plain recursion, you just think about the with the given sum step and just recur until you get to the 0 here, which is 1, and you plus it plus everything together, and you have a result. This shows successfully, but it will be very slow. A real example is this number. I can't even spell it, I pronounce it, but it took about 35 minutes to actually solve it. So it's actually really long, and with some really big number, it can take like hours to actually solve it. So it's unrealistic. So you actually can better it with space. So if you store the number, imagine having array with a 32 first result. So with these two property as the two trait, you already can calculate the first results. So with 32 first result like this, you imagine put in array, and instead of actually going to add 0 with 1, you can just go to add 14, add 16, add 13, and just going here because it's recursion. It keep minimize the number of the sum number. So this actually make it a little bit faster. However, it's improved a little bit, just still slow. Yet, there's actually a better way, which a lot of my peers actually apply it. It's run quite fast. Is using hash table. Hash table is you actually have to use pay, and you store the value. You use hash function to store it, and later you can access it with the recursion. So that's the way you improve it. It's actually not the best, quite fast as well, but I can make it better with math. So you calculate the sum of the first result, and can you notice the pattern? If you want to make some moment to actually think about it, you can pause it here. But there's a pattern. Firstly, you see number 1 got repeated, which location h to power, so h to power of k minus 1. So h to power 0 minus 1 is 0. So index, you imagine here like an array. So 0 here is 1. 2 to the power 1 is 2 minus 1, 1. So it will be the at location 1 will be 1. 2 about 2, 4 minus 3, 1, 3. So at location 3 is 1, and it being like that. You can see there is a pattern here. And between so 2 to the power k minus 1, there will be a palindrome. A palindrome basically the way you read it from forward and backward is the same. So it's basically symmetrical in another way to say it. You can see here, so this is symmetrical 2, it's also symmetrical 2, and if you spread it from on the left side, it's equal the same as you spread from to the right side. So it's the same. So now I will prove it with math, like how you can do how this thing actually true, not just some in the small instance like this. It's actually true for the whole thing. So we already have 2n plus 2 equal n plus 1 plus n, 2n plus 1 equal n. So you see that 2 to the power 2 minus 1 will always be an odd number. So it will be this case, 2n plus 1 n equal n. So if you continuously do it, you see 2n plus minus 1 will equal to 2 power k minus 1 will equal to 2 power k minus 1 minus 1. It will be exactly like that because an odd number, and keep being an odd number, it keep being like that until you reach the last number is 2 to the power 0 minus 1, when it's you cannot minus 1 anymore, and it will be h0, which is 1. So that's done. So prove the between a palindrome is a little bit difficult, but you can see it right now. So if you calculate, so right now the problem would be calculate the number between h up to the power k minus 1 and 2 to the power k plus 1 minus 1. So imagine you have a number like this. So if you have a number n that n is actually more than 0 or more to equal 0 and smaller than 2 to the power k minus 1 minus 1. The reason why it k minus 1, because you can see a pattern over here, is when you choose like 2 to power of 1 or 2 power 2, like so 0, 1, 2, so is it here, and the plus 1 would be here. So between these, we actually 4 number. If you imagine how I'm choosing n. So so it's plus 0, it will be here, plus 1 here, plus 2 here, plus 3 here, and the first one. So 4 number. This will have 8 number. So it actually equal so the largest number will be 2 power k minus 1 minus 1. So that's the way I'm gonna declare n. So the problem now we shift to finding the result of k 2 power of k minus 1 plus n. So you have an example like this when actually let k equal to 3, 1, 0, 1, 2, 3, so equal to 3. So here 2 power, so here is a position of 2 power k minus 1 is actually equal to 1 over here. Actually you can calculate later, and the job now actually find all the remaining number before you go to the next 2 power k minus 1, which be here would be k 2 to power of 4 minus 1. Now, so I divide into two cases. First, if n is an even number, so n belongs to this set 2, 4, 6, 0, 2, 4, 6. You can see, so it still use the same trace that 2n plus 2, because it's an even number will equal to n plus 1 plus n. So you have to make k minus 1 plus n to divide by 2, because it's right now being an odd number. Because even number is minus 1 over here, so 2 power of k here, the whole thing here is an odd number. So you actually have to illustrate 2 power 2 n plus 1 equal to n. So you can see over here, so you have whole thing minus 1 and divided by 2, and the final result will look like this. So 2 to power k minus 1 minus 1, the whole thing over here is the previous 2 per power k minus 1 before this number. So it's a range before that. So plus n plus, but it's plus n to divide by 2. So corresponding to value in this case, n divided by 2 will actually equal to 0, 1, 2, 3. So it's keep increasing like that. So you can see it in the example like this. So here 2 power of k minus 1 here. This actually plus 0 will equal to 2 power k minus 1 plus 0, which is this number. And then you go plus 2, it will be this position, equal to 2 power k minus 1 plus 1 over here. So with this number, and continuous, you can see the pattern, and you keep continuous to do that, and you fill half of it with an even number. Now it's an odd number, a little bit more difficult, but really fascinating as well. So here n will belong to this set 1, 3, 5, 7, and continues that. So because n is an odd number now, so 2 to power k minus 1 plus n will actually be an even number now. So even number will be 2n plus 2 equal to n plus 1 plus n. So we'll be two cases now. One is this, that's divided by 2, the whole thing divided by 2, and one is the whole thing minus 2 and then divided by 2. So here's the result. And I transform it into 2 power of k minus 1 minus 1. And here, so you actually can see how it's gonna relate it to the previous 2 to power k minus 1. So 2 power k minus 1 minus 2 power k minus 1 minus 1 plus n plus 1 divided by 2. This will be the same, but n minus 2 divided by 2. So that's going to be how this number going to relate it to the previous one. So corresponding to the value n in this case, you will have each pair. So the pair minus 1 divided by 2 and n plus 1 divided by 2 will be 0, 1, 1, 2, 2, 3, 3, 4, and just continue like that. So it actually be like this. So 4 plus 1, it will be 0, and 1 is the previous one, so 1, 3, so it will equal to 4. Next one, 3 will be 2, 3, so 3 plus 2 will be 5, 7, 2, 3, and sorry, 3, 4, so that'll be 2 plus 3 and 5. And this one, number 4, will be 3 plus 1 over here. So it's actually like say it's plain about yep. So and then it's the end of the result. So actually you can see a very fascinating trait here, because when it's to make it easy, you can imagine it's like an array. So here the index that equal to even number, we equal to the whole array before that. But the one in the odd number will equal to the sum of each pair here, and this will, as a consequence, it will be the sum of the two next number of this, one on the left and one on the right. So you can see this here. So it actually has a name. So this sequence actually calls third diatomic sequence, which based on Cooking-White tree, which is a tree that's going to list all the rational numbers. You can have a look online and you see a lot of different insight about it. So from this, I'm going to derive two properties that are going to help me how create my algorithm to solve the problem. Firstly, 2 power k minus 1 equal 1, which already show it. Let me this 2 power k minus 1 plus n will equal to k minus 1 n minus 1 and 1 plus n, which only when it's an odd number and n is larger or equal to 0 or smaller or equal to 2 power k minus 1 minus 1. This thing I already showed you and proved you in the previous session. But the real property I need is actually derived from this. Each range can be divided minus the midpoint. So imagine here, this range, the midpoint will be 2. So if you delete 2, the rest will be equal. Continue with this, you delete 2, the rest is equal, the same in the length. And the midpoint will be the sum of two current endpoints. So 2, it will be the sum of 1 and 1, which is current endpoint right now. And then each part can be divided the same. Yeah, because it is, because you can see the numbers will always be an odd number here. And when you minus this and divide it, it continuously be an odd number. Actually, you divide it here with even number plus the midpoint, it actually be an odd number again, and just delete it the same. Go ahead and you see that when you keep divided, you in the end you're going to have only one number left. But it was the same trait for the midpoint at that moment, which means the midpoint at that moment would be the sum of the two current endpoints. So you can see it here. So 2 is equal to 1 plus 1. So when you see on this range, 1 to 2, the midpoint will be 3. So 3 is 1 plus 2. Here the midpoint from 1 to 3 will be 4, is equal to 1 plus 3. 5 here will be 3 plus 2. So why is like that? Because you just think about it, because the whole number here is based on the previous number, and based on the previous number, and each previous number is the sum of the two current endpoints here. And when you actually keep going, this actually expand, got larger, and which number in between, you can just see it. So that's the trait. So give some thought about it. A little bit difficult, but it will be really easy to see. So based on that, let's create a solution. So with what you have right now, what is the best way to solve it? You can because you can divide it. Any thought? You can pause it and think about it. And here my idea: binary search, the best way and thing to do it. Because binary search, the time complexity is basically log n. So very good one. So here's the idea. So if you're not ready to see it, you can just pause it as well. But here, idea is have 3 steps only. Find the nearest 2 power k minus 1 on the left hand side sum set. This will be the start of the examined range. Continue with on the right hand side, and it will be the end of the examined range. So if you already have a range, you will run binary search to calculate the value of each midpoint until you calculate the value of the sum. So in other words, you actually using binary search to find the sum position in the examined range. Yep. So if you still want to think more about it, you just pause it here before I go to my pseudo code. So here's the pseudo code. So the function, so it will basically have two parts. One is the main one to actually solve it. So calculate the start position, assign value 1, because it was 2 power k minus 1, and position k minus 1, assign value 1. This is the first property we're going to use. So it also have one thing special. If star equal to n, return k plus 1. Because if these two equal, which means that the sum that's actually in form of 2 to the power of k. And if a sum in the form of 2 to the power of k, the final value would be k plus 1. It's always like that. And you actually can prove it based on what we already given. If you want to, you can give it a try and see how it goes. Or else you're going to return binary search with sum that start and end here. So you already have a range and the sum that you actually calculate it. And let's go. So here's the binary search. It will actually be recursion. So you have start position. If sum z equals start position, return start value. Sum z n will be return n value. It's a normal one when you try to search for it. But if not, which means the z is still in the range, you calculate the mid position and assign the value mid equal to start value plus n value. And if some z larger mid position, you only need to care about half of it, which on the right hand side. So you do the binary search with half of it. If else, it would mean on the left hand side, you only care about on the left side part. So that pretty much is pseudo code. If you still need a resolution, I will also post my real code on C# as well. You can see it in the link GitHub attached to this video. And that's all. Thank you. And if actually I can show you how it's gonna run. So here's my code. How run. So here my code representation. You can see on GitHub later. And right now if I run it, so I have linked my computer for quite a while, so it takes some time to actually set it up. So give us a sec. Ooh. Yeah. So yeah, really fast. So let me show you again. Run it. 1, 2, bang! Wow. It takes less than 4 seconds. And sometimes in my computer in good condition, it actually takes less than 2 seconds. All success. And you can see really huge number here, which all take less than 1 second actually solve it. Because we're using binary search, so it's only log n. And actually log n is just a way to say it. The way I use it, but the actually value of n actually is smaller. It's not actually real n. But for right now, the thing log n is really fast. You can see it with very huge number, but very fast. Nothing more than 1 second. And that's all. Thank you for listening.